Hello, I'm Maurice Dupre, and in this section we're going to discuss hyperbolic functions. In fact, we'll be discussing both the hyperbolic functions and their inverse functions, as well as all the derivatives of these functions. So let's begin with the first of the hyperbolic functions, the hyperbolic sine function. So for the hyperbolic sine, it's defined as e to the x over 2 minus e to the negative x over 2. So here is e to the x over 2. Notice it'll cross the vertical axis at height 1/2. And here's the negative of e to the negative x over 2. And so when you add those, you get a kind of an S curve here, and that is y equals the hyperbolic sine of x. So what we have is, in effect, e to the x minus e to the negative x, all divided by 2. That is the hyperbolic sine of x. Next, we have what's called the hyperbolic cosine of x. The hyperbolic cosine of x is e to the x plus e to the negative x over 2. And so I take e to the x divided by 2, e to the negative x divided by 2, add them up, and we get the hyperbolic cosine. So this is, it pictorially here almost looks like a parabola, but it's definitely not a parabola. Next we have the hyperbolic tangent. The hyperbolic tangent is simply the hyperbolic sine divided by the hyperbolic cosine, and so consequently for the hyperbolic tangent we would get e to the x minus e to the negative x divided by e to the x plus e to the negative x. And so that is our hyperbolic tangent. And so when we look at the picture of the hyperbolic tangent, it almost looks like the inverse tangent function that we see in ordinary trigonometric functions. Next, let's look at the hyperbolic secant. The hyperbolic secant, of course, is simply 1 over the hyperbolic cosine. Just like in trigonometry, secant is 1 over cosine. So the hyperbolic secant of x is equal to 2 divided by e to the x plus e to the negative x. So here we get a very interesting curve. It's like, almost looks like a bell curve shape. It's got this hump in the middle at height maximum point y equals 1. The maximum occurs right at x equals 0, and that's the hyperbolic secant of x. And then we have, finally, the hyperbolic cosecant of x, which is, of course, 1 over the hyperbolic sine of x. And so, therefore, we get 2 divided by e to the x minus e to the negative x. Now notice that's going to be 0 when x equals 0. We'd have e to the 0 minus e to the 0, which is 1 minus 1 or 0. So this expression is undefined at x equals 0, and so we expect to have a vertical asymptote at x equals 0. And in fact, as x is to the right of 0, e to the x is certainly bigger than e to the negative x, and so it's positive and will go off to plus infinity, whereas when we're over to the left of 0, e to the x will be smaller than e to the negative x, and the difference will be negative, and therefore we go down to negative infinity asymptotically as x goes to 0 from the left. We notice that all the hyperbolic functions are defined in terms of exponentials. Why do we call them hyperbolic sine, hyperbolic cosine, hyperbolic tangent, and so forth? Why are these trigonometric names coming in? Well, that's because of the identities that these functions obey. They're very reminiscent of trig identities. Let's look at these identities. The first identity is that hyperbolic cosine squared x minus hyperbolic sine squared x equals 1. Incidentally, as far as pronunciation is concerned, these are often read cosh and sinh. So you might say cosh squared of x minus sinh squared of x equals 1. The cosine h and the sine h, or cosh and sinh, are somewhat commonly used, and so those expressions become common, but we won't use anything like that for tangent h or cotangent h or cosecants or secant h and so forth. But for the hyperbolic cosine, we'll often say cosh, and for the hyperbolic sine, we'll often say sinh. So look at this first identity, cosh squared x minus sinh squared x equals 1. That's reminiscent of the Pythagorean identity from trigonometry, which says cosine squared x plus sine squared x equals 1. So the only difference is the appearance of a negative sign here instead of a plus sign. Here, this is sort of like our double angle formula from trigonometry. Hyperbolic sine, or sinh, of 2x equals 2 sinh x cosh x. Remember, the double angle formula from trigonometry says sine of 2x equals 2 sine x cosine x. Here we have what's reminiscent of the double angle formula for cosine. Cosh 2x is cosh squared of x plus sinh squared of x. Remember, the double angle formula for cosine is cosine 2x equals cosine squared x minus sine squared x. So again, we have the appearance of a sign reversal from what would be expected from trigonometry, but otherwise the identities are very similar. Here's the identity for cosh squared of x itself using the double, what's like reminiscent of the double angle formula. We get cosh squared x is 1 plus cosh 2x over 2. Remember, from trigonometry, cosine squared x is 1 plus cosine 2x over 2. And the formula for sinh squared x would be cosh 2x minus 1 over 2, whereas in trigonometry, sine squared x would be 1 minus cosine 2x over 2. So you see, other than a change in sign here, we have something that's almost identical to the situation for trig functions. Look at the corresponding situation for hyperbolic tangent and hyperbolic secant. We have hyperbolic tangent squared of x, or tan h squared x, equals 1 minus secant h squared of x, or secant h squared of x equals 1 minus tan h squared of x. Notice, if this were trig function, secant squared x equals 1 plus tangent squared of x. Over here for the hyperbolic cotangent, we have cotangent h squared x equals 1 plus the cosecant h squared of x. And notice in the trig situation, we would have cosecant squared of h is 1, cosecant squared of x is 1 plus cotangent squared of x. So again, we have a sort of a reversal of the situation, but somehow the pattern here is very similar to what happens in trigonometry. Let's look at a problem involving the relationship between the hyperbolic function and the natural logarithm function. Simplify 2 cosh of ln x in terms of exponentials. So remember, cosh of any expression u is e to the u plus e to the negative u divided by 2. So consequently, 2 cosh of ln x is equal to, well, the 2 cancels that 2 out of the denominator, and so we have e to the ln x plus e to the negative ln x. E to the ln x, of course, is simply x, plus e to the negative ln x of 1 over e to the ln x, and e to the ln x down there in the denominator is an x, so we have x plus 1 over x. Notice if I were to graph that equation, I'm graphing y equals x plus 1 over x, and we recognize right away that that's the graph of a hyperbola. Notice it's got a vertical asymptote at x equals 0 and oblique asymptote with slope 1. So the graph looks roughly, the oblique asymptote is y equal x, and so what we're getting is something that looks like this, a hyperbola. And so consequently, hyperbolic cosine. In other words, we call these functions hyperbolic functions because, in fact, when we compose these functions with the natural logarithm function, we do get functions which are made of hyperbolas. For instance, suppose I did the same thing for hyperbolic sine. We get 2 sine h of ln x is equal to e to the ln x minus e to the negative ln x, which is x minus 1 over x. So again, we're getting something which is, if we graphed it, we have a hyperbola. Well, when we compose the hyperbolic functions with the natural log, we find why they're called hyperbolic functions. Let's look. We saw that the hyperbolic sine of natural log x would be 1/2 of x minus 1 over x, and the hyperbolic cosine of ln x is equal to 1/2 of x plus 1 over x. And so consequently, if I take hyperbolic sine divided by hyperbolic cosine, I get x minus 1 over x divided by x plus 1 over x. Multiplying numerator and denominator through by x, I get x squared minus 1 over x squared plus 1. Turning that upside down tells me hyperbolic cotangent of ln x is x squared plus 1 over x squared minus 1. The hyperbolic cosecant of ln x is simply 1 over the hyperbolic sine of ln x. And if we take this expression and simplify it, we get 2x over x squared minus 1. And doing the same thing for hyperbolic cosine gives the hyperbolic secant of ln x is 2x over x squared plus 1. So now if we look at any one of these expressions, what we have is an expression that's built out of the hyperbolic sine or the hyperbolic cosine. Those two, when graphed after being composed with the natural logarithm function, give you a function whose graph is part of a hyperbola. Now let's look at the derivatives of the hyperbolic functions. Since the hyperbolic functions obey similar identities to trig identities, it shouldn't be surprising that the formulas for differentiating hyperbolic functions show similar patterns. Let's look. Derivatives of hyperbolic functions. The derivative with respect to x of sinh x is cosh x. That's just like the formula derivative of sine is cosine. The derivative of cosh x is sinh x. So here we have a slight change. The derivative of cosine x would be the negative of the ordinary sine of x, and so we don't have that minus sign. The derivative of hyperbolic tangent is hyperbolic secant squared. Well, that's just like in the trig case. Derivative of tangent is secant squared. Derivative of hyperbolic cotangent of x is negative of the hyperbolic cosecant squared. Again, that's just like in the ordinary trigonometry. Derivative of cotangent is negative cosecant squared. The derivative of the hyperbolic secant is the negative of the hyperbolic secant x times hyperbolic tangent x. The derivative of hyperbolic cosecant x is negative hyperbolic cosecant x, hyperbolic cotangent x. Notice we have negative signs in both of these cases, whereas in the trigonometry case, when you differentiate the secant of x, you get secant times tangent with a plus sign. What's going on here, remember, secant is related to cosine. Hyperbolic cosecant, hyperbolic secant is 1 over cosh. And so consequently, the fact that we didn't get a minus sign here is going to cause it to pop out over here. Sort of a conservation of minus signs is happening here. Well, in any case, with slight modification in terms of signs, notice we have very similar formulas for derivatives of hyperbolic functions as we do with derivatives of ordinary trig functions. Well, let's work a differentiation problem where the function involves the hyperbolic tangent. Here I have y equals 2 times the square root of t multiplying the hyperbolic tangent of the square root of t. So to differentiate, dy dt equals 2 times the derivative of square root t, that's 1 over 2 square root t, times the second factor hyperbolic tangent of square root t, plus 2 square root t times the derivative of the hyperbolic tangent of square root t. Well, the derivative of hyperbolic tangent is hyperbolic secant squared. And so we get hyperbolic secant squared of square root t. And of course, by the chain rule, we have to multiply this by the derivative of square root t, which is 1 over 2 square root t. So we have the hyperbolic secant squared of the square root t, all of this being multiplied by 1 over 2 square root t, and of course we have our factor 2 root t in front, and of course now we see that cancels that, the 2's cancel here, and so finally dy dt is simply 1 over square root t times the hyperbolic tangent of square root t plus the hyperbolic secant squared of square root t. Well, we've seen that hyperbolic functions composed with the logarithm functions simplify and give functions whose graphs are hyperbolas. Let's differentiate the other way. Let's differentiate the logarithm of a hyperbolic function. So here I want to differentiate the natural log of sinh z. That's the natural log of the hyperbolic sine of z. So remember, the derivative of natural log of u with respect to x is 1 over u du dx. And so consequently, dy dz here is equal to 1 over hyperbolic sine z times the derivative of hyperbolic sine z. Well, that's hyperbolic cosine z. And so we get cosh z over sinh z, which is hyperbolic cotangent z. So the derivative of natural log of hyperbolic sine of z is the hyperbolic cotangent of z. Well, we've looked at the hyperbolic functions and their derivatives. Now let's consider the inverse hyperbolic functions. To begin, let's look at the inverse of the hyperbolic sine function. Here we're looking at y equals the inverse sinh x, that is the inverse function to the hyperbolic sine. That equation, of course, is equivalent to the equation x equals hyperbolic sine y, or x equals sinh y. Now, here is the hyperbolic sine curve, or y equals sinh x. And so here's the diagonal line y equal x, and if I reflect this curve through the diagonal, we get the graph of y equals hyperbolic sine inverse of x, or y equals sinh inverse of x. Notice it's defined for every real x. And as x goes to infinity, this goes off to an infinite value, and likewise in the reverse direction, as we go to negative infinity, sinh inverse of x will approach negative infinity. Now let's look at the hyperbolic cosine and its inverse. Remember, the hyperbolic cosine is this sort of parabolic looking curve, and so consequently it's not 1-to-1, but it is 1-to-1 for x greater than or equal to 0. So restricting the domain of cosh x to x greater than or equal to 0, we get a function which is 1-to-1, and we reflect that in the diagonal line y equal x, getting this curve, which, you know, it kind of is reminiscent maybe of square root x minus 1. It looks sort of parabolic, like a square root function, but it's not. It's y equals cosh inverse of x. Now let's look at the hyperbolic tangent. If I graph the equation x equals hyperbolic tangent y on this coordinate system, then I'm really graphing y equals the inverse function to the hyperbolic tangent of x. That is, y equals hyperbolic tangent inverse of x. And since the actual hyperbolic tangent was the S curve coming up like this, when I invert it, I get a curve which actually sort of is reminiscent of the tangent function itself. Now the tangent function would have vertical asymptotes at negative pi over 2 and pi over 2. This one has vertical asymptotes at negative 1 and 1. So notice it's only defined for x between negative 1 and 1. That is, the domain here, in this case, has to be negative 1 less than x less than 1. Now let's look at the hyperbolic cotangent. Its domain is sort of the opposite to the hyperbolic tangent. Now I have to have absolute value of x greater than 1. So for instance, if I were to put the hyperbolic tangent in here, we would get this curve. That's the inverse of the hyperbolic tangent. And so the two together actually form a function which is defined on almost the whole real line. That's everything except the points negative 1 and 1. So here's the cotangent H inverse. Here's the tangent H inverse. Now let's look at the graphs of the inverse functions to the hyperbolic secant and the hyperbolic cosecant, and then we'll look at the derivatives of all the inverse hyperbolic functions. So remember, the hyperbolic secant's graph was a sort of a bell curve shaped graph with its maximum value 1 here at x equals 0. So y equals secant hx is not 1-to-1, but if we restrict its domain to x greater than or equal to 0, then it is 1-to-1. And so when I reflect that in the diagonal line y equal x, we get this curve, which is sort of like half a bell-shaped curve in the vertical direction. So notice the domain of the inverse hyperbolic secant is only 0 less than x less than or equal to 1. So the domain here is now 0 less than x less than or equal to 1. Now finally, let's look at the hyperbolic cosecant and its inverse. Here we get something that looks sort of hyperbolic, and the graph here is, of course, undefined at x equals 0. One thing that you might notice here is that the graph of the inverse hyperbolic cosecant function has the same basic shape as the function itself. That's because if I reflect these curves through a diagonal line with slope 1, notice it's just going to flip them like this, which really doesn't do much. So you might think they're equal to their inverse functions, but in fact they're not. There are subtle differences here in the curvatures and so forth. Well, now let's look at the derivatives of all the inverse hyperbolic functions. The derivative of hyperbolic sine inverse, that is the derivative of sinh inverse of x, is 1 over the square root of 1 plus x squared. Notice that in the case of sine inverse, we would have the square root of 1 minus x squared, so we have a difference in sign from what would happen with the inverse sine function. If I look at the derivative of cos inverse x, I get 1 over the square root of x squared minus 1, which is more reminiscent of what you get when you differentiate a secant function. But in any case, it's not the same formula as the derivative of the secant, since that would put an x out in front, or an absolute x out in front of that radical. So you have x, we could look at it as, in this case of the hyperbolic sine inverse, we have x squared plus 1, and for cos we have x squared minus 1. How about for the hyperbolic tangent inverse of x? Its derivative is 1 over 1 minus x squared, and of course that will only be valid for absolute x less than 1. Certainly we have a problem there when absolute value x equals 1, since we'd get 0 in the denominator. And look, when we take the derivative of the hyperbolic cotangent inverse of x, we get exactly the same expression, but with the restriction that absolute x be greater than 1. So remember, we looked at the graphs of these two functions, the hyperbolic tangent inverse and the hyperbolic cotangent inverse, and saw that they could be put together to make a function that was defined on the whole real line, except that x equals plus and minus 1. And notice when we differentiate that function, we get simply 1 over 1 minus x squared. Now the derivative of the hyperbolic secant inverse of x is negative 1 over x times the square root of 1 minus x squared, and that's only valid for x between 0 and 1, strictly between 0 and 1. And remember, the derivative of the secant inverse would be absolute x times the square root of x squared minus 1. So what's happened here is we have a reversal of the sign of what's inside the radical. The derivative with respect to x of the cos inverse of x is negative 1 divided by the absolute value of x times the square root of 1 plus x squared, and that's for all x not equal to 0, the derivative of cos inverse of x. So notice that here we're getting something that is more reminiscent of the derivative of secant inverse x, except that instead of having x squared minus 1 inside the radical, we have 1 plus x squared. So all told, we're getting very similar expressions to the derivatives of inverse trig functions. And so together with inverse trig functions and inverse hyperbolic functions, we can get functions whose derivatives are just about any type of a radical involving a 1 plus or minus x squared or x squared plus or minus 1 and so forth. Now, some of the relations here can be seen to be the result of these simple identities for the inverse hyperbolic functions. The hyperbolic secant inverse of x is cos inverse of 1 over x. The hyperbolic cosecant inverse of x is sinh inverse of 1 over x. And the hyperbolic cotangent inverse of x is hyperbolic tangent inverse of 1 over x. These are sort of a little bit reminiscent of the identities for the inverse trig functions, which involved trig function or co-trig function inverse of x equals pi over 2 minus trig function inverse of x. In any case, it allows you to get an equation which relates the derivative of each one of these inverse functions to the derivative of its co-function inverse. Let's differentiate a function that has an inverse hyperbolic function in it. Here I want to differentiate the function hyperbolic sine inverse of the tangent of x. So we remember that the derivative of the tangent of x is secant squared of x. And so we're going to have to differentiate by the chain rule. The derivative with respect to x of hyperbolic sine inverse or sinh inverse of any function u of x is 1 over the square root of 1 plus u squared times du dx by the chain rule. And so consequently what we have here is the case where u is tangent of x, and so du dx is secant squared. And so all I do is replace the u here by tangent of x and the du dx here by secant squared x, and I get the answer, the derivative with respect to x of sinh inverse of tan x equals 1 over the square root of 1 plus tangent squared x times secant squared x. Now remember from trig identities, 1 plus tangent squared x is secant squared x. So down here I have square root of secant squared x. So what's that? That's secant squared x divided by absolute value of secant x. On the other hand, secant squared x is the same as the absolute value of secant x squared, and so canceling, we just get absolute value of secant x finally as the answer. Well, we've looked at the hyperbolic functions and their inverse functions and seen how they're very similar to trig functions and trig functions inverses. You might want to look carefully at the patterns involved because there's no way around it. If you have to deal with these functions a lot, you're going to have to memorize all the formulas. So now that you've seen some problems worked and looked at these formulas, you should study them and practice on your own.